So here I want to show you how to use the inverse of the coefficient matrix to solve a system of linear equations. And the overall theory is that if you have a system of linear equations, ax equals b, where a is your coefficient matrix, x is your unknowns vector, and your b is your right-hand side vector, you can solve for your unknown vector, your solution vector x, as the inverse of the coefficient matrix times the right-hand side vector. So today I want to use this system of 3 equations and 3 unknowns to demonstrate how we will do this in this class. And the way we're going to find the inverse is by augmenting an identity matrix, then using Gaussian elimination to get the reduced row echelon form of that large matrix, and then we'll just do the matrix multiplication on our inverse matrix to get our solution vector. So the first step is to take our coefficient matrix from the system of equations and augment on an identity matrix. So here we're just going to take the coefficients from our equations, 1, 2, 3, and we don't need to worry about our right-hand side, we'll just worry about our coefficients, 1, 0, 1, and 1, 1, negative 1, and then we augment on the appropriate sized identity matrix. So here are 3 by 3. So 1, 0, 0, 0, 1, 0, 0, 0, 0. And now we're going to use Gaussian elimination to get the reduced row echelon form of this matrix. So you might want to go back and review the Gaussian elimination strategy from the previous video or a previous video somewhere. But we're going to follow those steps to get the reduced row echelon form of this matrix. So the first step is always to find the pivot element. So here it'll be the first row, first element, and then do row reduction to get zeros everywhere else in that column. So here are row 2 new. We're using the equation from up over there is the R2 old minus the element in that column of the row we're doing row reduction on. So 1 divided by our pivot element 1 times our pivot row 1. And our R3 new will equal R3 old minus the same 1 over 1, because we have a 1 here, not because of row 2, but the 1 in row 3, times row 1. And so this gives us a new matrix. We did nothing to the first row, so it'll still be 1, 2, 3, 1, 0, 0. I'm going to get rid of the augment sign for now. 0, negative 2, negative 2, negative 1, 1, 0, 0, negative 1, negative 4, negative 1, 0, 1. And now our second pivot element is the negative 2. So the next row, so we did row 1, now we're going to do row 2. The first column with non-zeros here or anywhere below. And this is where we might think about doing row interchange if we had a larger magnitude value somewhere in this column below. But here, negative 2 is the largest magnitude between negative 2 and negative 1, so no row interchange is needed. And now we'll say our row 1 new is our row 1 old times the 2 divided by negative 2. So minus 2 divided by negative 2 times row 2. And our row 3 new is our row 3 old minus, and now we have a negative 1 divided by negative 2, so minus 1/2 of row 2. So my new matrix now, I have on the first row 1, 0, 1, 0, 1, 0, and then I have 0, negative 2, negative 2, negative 1, 1, 0, and the last row I have 0, 0, 3, negative 3, negative 1/2, negative 1/2, and 1. And now we're going to do our last row of reduced row echelon pivoting. So we're going to find our pivot element, that first non-zero element, and then we're going to do our row reduction. So row 1 new now is my row 1 old minus, now we have in row 1, 1 divided out by our pivot element negative 3, row 3, and our row 2 new will equal our row 2 old minus -2 divided by -3 times row 3. So 2/3 of row 3. And doing this, now my matrix, I have 1, 0, 0. So we're looking for those zeros in the rest of that column. And then -1/6, 5/6, and 1/3. And then the next row, I have 0, -2, 0, and then -2/3, 4/3, and -2/3. And then my last row, I have 0, 0, -3, and then I have -1/2, 1/2, and 1. And then the last step to get to our reduced row echelon form is to divide each row by the leading non-zero entry. So row 1 will divide by 1, row 2 will divide by -2, and row 3 by -3. So after doing this, that will get 1, 0, 0, -1/6, 5/6, and 1/3, and then 0, 1, 0, +1/3, -2/3, and +1/3. And then our last row, 0, 0, 1. So what we're really looking for is to get that identity matrix on the left-hand side now, and we've achieved that. And then the last element's 1/6, 1/6, and -1/3. And after doing that Gaussian elimination to get the reduced row echelon form, the right-hand side of this matrix is now my A inverse. So right here, here's my A inverse. So using that, I can now solve for my solution vector by multiplying that by my right-hand side. So my A inverse from all of that, augmenting the identity matrix, reduced row echelon form, is the right-hand side of that final matrix. So -1/6, 5/6, and 1/3. And then 1/3, -2/3, 1/3, and then 1/6, 1/6, and -1/3. So that's our inverse. And then we'll multiply this inverse by our right-hand side vector to get our solution vector. So we will say our solution vector x is that A inverse times our right-hand side vector. So that's just the coefficients here, 2, 3, 1, to get our solution vector. So our solution vector here, x, to do our multiplication, remember, take these, rotate them, and multiply them. So we have -1/6 times 2 plus 5/6 times 3 plus 1/3 times 1 will be x1. And then x2, I have 1/3 times 2 plus -2/3 times 3 plus 1/3 times 1. And then my last x3 will be 1/6 times 2 plus 1/6 times 3 plus -1/3 times 1. And if we do all of that math, the solution vector now should be equal to 5/2, -1, and 1/2. And if you plug that into your original system of equations, should get that solves this system. So big approach here, we took our coefficient matrix, augmented on a 3x3 identity matrix. We did Gaussian elimination to get down to our reduced row echelon form, where we had identity matrix then on the left instead of the right, and our inverses on the right-hand side. Take that, multiply by the right-hand side vector, and you should get your solution vector.